All right, we are now into linear algebra. Let's go ahead and check Anki. Yeah, we got something. What are the 9 chapters of linear algebra? All right, of elementary linear algebra, Anthony and Call. Sequences of linear, sequences of linear equations. Yeah, sequences of linear equations and matrices, determinants, Euler vector spaces, general vector spaces, eigenvalues and eigenvectors. Diagonalization in quadratic forms. Dang it. That's one. We got 3 more. The last one is general linear transformations. Numerical methods, general linear transformations, numerical systems, diagonalizations, and product space, linear product space, general product space, inner product space, okay, here we go. We got the first 5. Inner product space, diagonalization in quadratic forms, general linear transformations, numerical systems, numerical methods. Okay, systems of linear equations. I said sequences. Systems of linear equations and matrices, determinants, Euclidean. I say Euclidean vector spaces, general vector spaces, eigenvalues and eigenvectors, inner product spaces, diagonalization in quadratic forms, general linear transformations, and numerical methods. That was very close. I'll say hard. All right. What did we learn about yesterday in linear algebra? Well, it would have been complex number stuff. We're in Appendix B still. What would we have learned yesterday about complex numbers? Complex numbers. Okay. Something's coming back. No? Yes, polar form. All right, so we've got complex plane. We're graphing the vector of a complex number. That angle formed between the complex number and the positive real axis, there's an angle there, and then we can basically use trig on that. So if we say that the length of the diagonal is the absolute value of z, well, then we can say that the real part of the the length of that vector, the real component of the vector, is absolute value of z times cosine of the angle. And the same thing for that vertical aspect of the vector, aka the imaginary part of the vector. We can call that absolute value of z times sine of the angle. Cool? All right, what else we got? Oh, so therefore we can say polar form is z equals, so typically complex numbers in the form of z equals a plus bi. Well, we can say the polar form is z equals the absolute value of z, parenthesis, cosine angle plus sine angle times I, parenthesis. That's the polar form. All right, polar form, cool. We would have gone over those formulas, and that's because the formulas we're getting at, and we got some theorems as well based on the reciprocals and the conjugate, the definition of the reciprocal and the conjugate. But to divide z1 over z2, assuming that z2 is non-zero, we basically just multiply the numerator and the denominator by z2, I believe. I say complex number, right? Yeah. Got that part. Do we do anything else? No. Okay, we got that all. All right. The argument. The argument is the angle that is formed between the real axis, positive real axis, and the vector. And there's only one central argument. Not central argument. Yeah, central argument. No. Principal argument, and that is in between pi and negative pi, because you can just add 2 pi plus or minus as many times as you want. It's the same angle technically, but we're only looking for the principal argument. Yep. All right, that's it. That's all we did yesterday. Okay, there's a lot of thinking then. So geometric interpretation of multiplication and division of complex numbers. Whatever the hell that means, we're going to be in that now, so I'll be back in a second. All right, guys. Makes sense. Basically, geometric interpretations of multiplication and division of complex numbers. Geometric interpretations mean like when we're graphing in the complex plane, what changes, what happens? Well, when multiplying two complex numbers, essentially, you're just going to multiply the moduli of both. So it gets longer or shorter based on the moduli of both of these, or the absolute value of both of these two complex numbers. How do we find the complex that? Well, we times basically complex number times its complex conjugate will get you the absolute value squared. So it's basically the square root of a squared plus b squared, Pythagoras theorem, to find the modulus or the absolute value of a complex number. So two of them times. So the geometric interpretation of multiplying complex numbers, right? Essentially, the geometric interpretations are going to multiply the moduli together to get the new moduli, new modulus, and you're going to add the arguments together. That's it. And for division, you're going to divide the moduli by each other and then subtract the arguments. That's simple. And then there's a little note at the end of this after they worked an example that, the complex number I has a moduli of 1 and an argument of 90 degrees or pi over 2. And so if you multiply I by a complex number, it's not going to change the actual length of the vector or change the value of the modulus. It's just going to shift it 90 degrees counterclockwise. So that's it for that. Now we're going to be into de Moivoir's formula. I don't know if that's how you say it. De Moivoir's. It looks French to me, Moivoir. I don't know if that's how you say it, but de Moivoir's formula. Let's do it. I'll be back in a few quick seconds. All right, that was pretty simple. Let's see if I can pull it all out. De Moivoir, French. I knew it. I've taken French. I knew that it looked French, the Oivre. Anyway, so extending from that interpretation, that big geometric interpretation of multiplying a complex number. So we say, what about a complex number to the nth power where n is a, say, positive integer and z is a non-zero complex number. So you're basically taking a complex number to a power of n in which n is a positive integer. Well, we just learned that when you multiply complex numbers, you're basically just multiplying the moduli together and adding the arguments. So z to the n is going to be, it should be the absolute value of z to the n power. And then within parentheses, that all this is going to be multiplied by cosine times n times the angle, the argument, so number of arguments, parenthesis plus I times sine times n times the argument, parenthesis. Is that all correct? Yeah, that is all correct. So then, in the unique case where the modulus is equal to 1, the formula simplifies to z to the n equals, we don't have to put the absolute value of z to the n power because that's just going to all equal to 1. So z to the n equals cosine n times the argument plus I times sine of n times the argument. And then using the polar formula from there, we can extrapolate. And so we substitute cosine argument plus sine, or plus I times sine argument. That's the polar form. We plug that in for the original z. So that to the n power equals cosine n times argument plus I times sine n times argument, right? So when you've got a complex number in its polar form to the nth power, and the modulus is 1, you're going to be equal to simply taking that exponent and just moving into multiplying it by each of the arguments. Pretty simple, I guess. As far as the basics go. I mean, that was discovered in this guy lived in 1667 to 1754, so this is pretty old shit. Well, we've got 5 more minutes. All we've got left is Euler's formula in this Appendix B. I guess I'll try to get through this and call it a day, and we'll see. I'll be back in a sec. All right, wrapping up for today. This last section was about Euler's formula and basically complex exponentials. So when you have a complex number or imaginary number or complex number in the exponential. And so Euler's formula is basically e to the I theta equals sine theta or cosine theta plus I times sine theta. Is that right? Weird. That's just okay. Yeah. Interesting. Yeah, that is right. That's Euler's formula. And they're basically just talking about how to manipulate when you have a complex number with an imaginary part in the exponential, and how that still follows the standard exponential rules. So e to the z, which z is a complex number, you can rewrite as e to the a plus bi, right? And then we can split those using exponential law to ea times e to the bi. Is that right? Then how do we get that down? Yep. Okay, that's how you do it. So then that somehow that works out to be e to the a times parenthesis cosine b plus I sine b. Let me think. I'm not exactly sure why that's the case. There's some kind of exponential rule, surely. Oh, when you're multiplying exponentials. Anyway, that's that. That part is a little hazy, purple hazy, but I gotta go pretty quick here. So today we covered de Moivre's formula, Euler's formula, complex exponentials, and geometric interpretations of complex numbers, dividing complex numbers, geometric interpretation of dividing complex numbers, and multiplying complex numbers. And that's going to wrap it up for today. Talk to you guys tomorrow. That's done. Appendix B is done. Appendix B is done. Let's go. Now we can actually go into chapter 1, which is systems of linear equations and matrices. So pretty excited for that. Let's go. All right. Talk to you guys later. See ya.